friends. Today we're talking about ionic compounds, what they are, and their properties for the ionic bonds mini unit. So the first thing is important that ionic bonds are a type of chemical bond, and you have to understand what a chemical bond is. Chemical bond is a force that holds two atoms together, any two atoms. It could be two of the same atoms, it could be a metal and a non-metal, or a metal and a metal, or a non-metal and a non-metal, and those are all chemical bonds. It may be from between the positive nucleus and negative electrons, or a positive cation or a negative anion. That is one type of chemical bond that is called an ionic bond. When you're sharing electrons, that is called a covalent bond, and when it's two metals, it's called a metallic bond. So how do you form a positive ion? Well, the first thing that you have to realize is that electrons are negative. We've been talking about electrons for a while now in the atom, and electrons are negative. So when you lose something that is negative, you become more positive. So a cation, meow, is pause, meow, positively charged. Think of cats have paws, so they're positively charged. They lose or give electrons to form a stable octet of valence electrons. So always remember 8 is great. So, and these are primarily in rows 1, 2, the transition metals, and 13. So alkaline metals, alkaline earth metals, the transition metals, and the boron family. They lose electrons to mimic a noble gas. So it's easier for them to lose 3 electrons and look like the noble gas in the row or period above, think about your noble gas formations, than to gain more and look at the noble gas in the row that they're currently in. And the reactivity of the metals is based on the ease in which they give up the valence electrons to form a stable octet. Remember, row 1 is the most reactive, row 2, sorry, not row, period. Period 1 is the most reactive, period 2 is slightly more reactive, transition metals are kind of reactive, and period 13 aren't, column 13 aren't super reactive. Okay, so let's talk about negative anions, or ions. They're called anions. They're negatively charged ions. These are ions or elements that gain electrons. So when you're gaining a negative, you're going to become more negative to form a stable octet. They gain their valence electrons. They gain electrons to mimic the noble gas in their same row or period. So these are primarily columns 15, 16, or 17, or the nitrogen family, oxygen family, or halogen family. And again, the reactivity of the nonmetals is based on the ease in which they gain their valence electrons. So nitrogen, not as reactive as oxygen, not as reactive as the most reactive, which are the halogen family. So let's think about the formation or nature of ionic bonds. There's some basic rules in which they live by, or you can lose and gain by. The first rule is you can only lose the number of valence electrons. So alkaline metals can only lose 1 because they have 1 valence electrons. Alkaline earth metals can only lose 2 because they have 2 valence electrons. The transition metals, or those common copper ion, the common metal ions that you were given, they can only lose or gain what they were given. So copper 2 can only lose 2, copper 1 can only lose 1, iron 3 can only lose 3, and so on. Elements with more than 4 valence electrons primarily gain additional electrons, and they can only gain as much as it takes to make 8. So column 15 with 5 valence electrons gains 3, column 16 with 6 valence electrons gains 2, column 17 with 7 valence electrons gains 1. And the number of electrons lost must be equal to the number of electrons gained. That is specifically for making bonds. So you can't have one that gains 3, but they're only trying to give 1, that type of item. So we will go more into that in a second, but that is a really good rule to know. Number of electrons lost must be equal to the number of electrons gained. Number of electrons gained must be equal to the number of electrons lost. So here's your charges cheat sheet. Column number 1 forms a cation, and that's a 1+ ion. Column number 2 also forms a cation, and that's a 2+ ion. Your transition metals are all cations. They have multiple charges, also known as oxidation state. So if you hear the word charge or oxidation state, they mean the same thing. They are synonyms. And it must be provided for you if it's in a name in Roman numerals. So 1+ is 1 in Roman numerals. 2+ is 2 in Roman numerals. 3+ is 3 in Roman numerals, and 4+ is 4, which is IV in Roman numerals. Please remember, Roman numerals are all caps, and they are capital I's, not lowercase l's. They are capital I's and not lowercase l's. Here's some worksheets. Column 13 is still a cation. It's got a 3+ charge. Column 15 forms an anion with a 3- charge. 16 forms an anion with a 2- charge, and 17 forms an anion with a 1- charge. Here's another important thing. Notice that there's no column 14. Column 14 kind of plays by its own rules. There's a few elements in column 14, like tin and I believe lead. Let me, hold on. Tin and lead, I was exactly right, that act like transition metals. So you would have to use Roman numerals with them. Other than that, they do not form any cation or anion. They only form transition covalent bonds. So if we're looking at how you would look at an electron configuration, because we were just doing electron configurations on how to determine ionic bonds, let's make potassium fluoride, that's Kf. So if you find K on your periodic table, you notice that it has 1 valence electron, that's in 4s1. If you were to do this in noble gas formation, that would be argon, that's 1s2, 2s2, 2p6, 3s2, 3p6 is argon, 4s1. Fluorine, on the other hand, is 1s2, 2s2, 2p5, or in noble gas formation, helium, 2s2, 2p5. So they each want to look like a noble gas. So if you look at potassium and fluorine, they're both really close to a noble gas formation. Potassium, if you're thinking of noble gas formation for the noble gas configuration, just needs to lose at 4s1 to mimic argon. Fluorine, on the other hand, has to gain 1 to mimic neon. So what they legitimately do is potassium gives fluorine their extra valence electron. So that's why potassium loses 1, and look, 4s1 went away and they became a 2p6. So they lost this one and they gained 1 here. So this one went there. And so when you look at it, the 4s1, it became 3p6, 3p6, and then 3p6, 2p6. So now they both look like valence noble gases. Potassium has lost its valence electron by giving it to fluorine. So now everybody is happy because they mimic noble gases now. I know I did these in full electron configuration form. I'm going to throw up some information later and show you how to look at this in noble gas form, because I believe that is an easier form to understand that. And I apologize for not having that done quite now, but I will throw a sheet up later to have that done for you. So let's talk about properties of ionic compounds. So once you have an ionic compound, what are they? Are they high melting points, low melting points? How can you determine through testing whether it's an ionic or covalent compound or any other type of compound? So here's the first thing. It's always made up of a metal and a non-metal. And the metal always is written first. So it's cation plus anion, metal plus non-metal. Remember, your cations are always metals. Your non-metals are, your anions are always non-metals. And then they form an ionic crystal. This is the regular and repeating pattern into which the positive and negative ions are packed. So you're thinking about like batteries or magnets. You have a positive, and it doesn't want to be right next to another positive. It wants to be next to negative. So you go positive and you surround it by some negatives, you know, depending on how many positives you have. And you do negative, positive, negative, and they fit it into this crystal so that the positives are never right next to the positives and the negatives are really never next to the negatives. But they fill it in such a way that it reduces space, because that's why there are different types of ionic crystal shapes depending on the compound. Some are more complex, some are really easy, and that leads to the crystal lattice. Keeping in mind that each positive ion is surrounded by negative ions, and each negative ion is surrounded by positive ions, because just like magnets, positive does not want to be by positive and negative does not want to be by negative. Your crystal lattice leads to your lattice energy, which we will talk about in 1 second. But let's talk about some more properties of ionic compounds. The color of ionic compounds is always related to their structure. They have high melting and boiling points, and that how high is dependent on the strength of their lattice structure. The higher the melting and boiling point, the stronger the lattice structure. And the structure is based on brittleness and hardness is also based on the strength of lattice structure. So very brittle compounds might have a very strong structure, a very hard compounds might have a structure. That is why a lot of alloys are important, because getting in some of those other compounds helps to prevent the brittleness. So due to the fact that charged particles must be free to move to conduct electricity, it's not conductive in a solid state. So solid ionic compounds are not conductive of electricity. But we've all heard of electrolytes. They're in Gatorade, they're often in like Sprite and everything else. An electrolyte is an ionic compound whose aqueous solution conducts an electric current. And I was talking about earlier about lattice energy. And this is the energy required to separate 1 mole of the ions of an ionic compound. 1 mole is just a measurement. So 1 mole is like saying 1 unit of the ions of an ionic compound. So the stronger the lattice energy, the harder it is to pull apart. But lattice energies aren't measured in how positive they are, they're measured in how negative they are. So it's important to note that the more negative the lattice energy, the stronger the energy is. So it's going to be harder to pull apart. It's going to take more energy to pull apart a very negative lattice energy than a very non-negative lattice energy. So let's look at some examples. So sodium fluoride, these are all negatives, but they don't necessarily write them in negatives because they know that they're negative. So it's kilojoules per mole is what lattice energies are measured in. So sodium fluoride is negative 926 versus aluminum oxide, which is negative 15,900. It's going to be easier to pull apart sodium fluoride than aluminum oxide. And you can look at these. You have some very high numbers, you have some very low numbers, and that is how you can rank how strong the energies are for lattice energies and how strong the bonds are. So this is the beginning of ionic compounds. Thank you so much for listening.